Alright, this is video 3 for the electrostatics unit. In previous units, we've talked about force, and we've talked about potential energy. We've also talked about conservation of charge. So in this one, we're going to introduce something new. This is something that you have not seen. This is called electric potential. Electric potential is the electric potential energy per unit charge. So if I looked at a battery, I could take a look at how much electric potential or electric potential energy each charge has for that battery. Informally, this is called voltage. So if I had a 9-volt battery, that means that I would have 9 joules of potential energy for every coulomb of charge stored in that 9-volt battery. So for the time being, we might call this just potential. So the potential, or the electric potential, is measured with a volt. Now, a warning here, electric potential energy and electric potential are two different things. They each have their own unit. Electric potential energy is measured with a joule, where electric potential is measured with a volt. So 1 volt will equal 1 joule per coulomb. This was named after Italian scientist Alessandro Volta. So the formula for electric potential, the way we calculate this, it's kind of unfortunate we use a capital V. I'll put some blocks on this just to differentiate it. So electric potential equals the electric potential energy per unit charge. So let's say I have like a Van de Graaff machine, something that I build up charge on, and I take a little tiny test charge. So a little test charge Q. What I'd like to do is I would like to calculate what the electric potential is at that little space, or that little region in space. So since electric potential is the electric potential energy per unit charge, remember that electric potential energy is coulombs constant times the first charge times the second charge over R. So in this case, R would be the center of the big Q to the center of the lowercase q. So I'd have my electric potential energy, KQQ over R, and then I would divide that by my charge Q. So we can see then that the way we calculate electric potential is coulombs constant times the charge of the thing we're studying divided by R. So R is the distance from the center of the thing we're studying out to where we're measuring the voltage or the electric potential to. Now, when a point charge moves from one location to another inside an electric field, it will have a different electric potential at the first point than it did at the second. So by subtracting the two potentials at those 2 points, we get something called the electric potential difference, or potential difference. So here we have some object that has a charge of Q, and I'm going to take a point charge. I'm going to move it from this location to that location. So I would have, let's say, an initial position, and then a final position. So what I could do is I could find the potential difference, which would be the potential at location 2 minus the potential at location 1. So I'd have a potential at this location, and then I would have a potential at that location. And hopefully you can see that this distance between where I move the point charges would be like a delta R, final position minus initial position. And taking a look at what we've done before, the only thing changing is delta R. So to get that potential difference, I would simply have KQ over the change in position. Now this is going to introduce an electric force acting on a charged particle. And the force is always directed toward regions of lower electric potential energy. So if I were to think about this, let's say that this Q is a positive charge and this test charge is positive as well. So I have two positive charges. If I take a look at the model for electric potential energy, K QQ over R, notice that as I get farther and farther away from this charge, the electric potential energy decreases. And since these are both positively charged test charges, or this is a positive test charge, notice as I get farther and farther away, the electric force in all directions will point away from that capital Q, that big charged object. So that force is pointing in a direction of lower electric potential energy, or lower electric potential. The next thing we need to talk about is the principle of superposition. And what this is, it's something that we can apply to electric potentials. We can also kind of apply it to electric potential energy, but it's easier to apply it to electric potential. And basically, we can think of electric potential as a scalar. So all we really need to do is add the different electric potentials up. So let's work on an example so you can see how that works. So let's say we have three charged objects placed on the corners of a 2 by 2 meter square. The top left has a charge of -2 coulombs. The bottom left has a charge of +3 coulombs. And the bottom right has a charge of -1 coulomb. And again, this is a 2 meter by 2 meter square. What is the electric potential at the top of the right corner? So what would that potential equal right there at that top corner, where there's no charge there, but I just want to know what that would equal. So basically all we need to do is just calculate the electric potential for each of those three charges and then add it together. So I'm going to call it's -2. I'm going to call this one Q1, Q2, and then Q3. So the potential from particle 1 would be K Q1 over, now if we think about particle 1, it's 2 meters from particle 1 to that corner. So K is 9 billion. And that's Newton meter squared per coulomb squared. Q1 is -2. This time you do want to leave in the negatives for 2 meters. And we can see that we get -9 billion volts. Okay, so for the second one, the distance from here to here would be about 2.83. Yeah, just right triangle it. You got 2 by 2, and then it's a right triangle, find the hypotenuse. So this would be like 9 billion newtons meters squared per coulomb squared times positive 3 coulombs. Divide that by 2.83 meters. So getting positive 9.54. And then for 3, yeah, let me clean this up. So for that one, we'd probably get what, 4.5? Negative 4.5. So that volt, or the voltage at that position then, would be the sum of those 3. So I'd have my negative 9 billion plus this 9.54 billion minus that 4.5 billion. So at this point, I get negative, and it's okay to get negative voltage, 3.96. What about the potential difference? What would I compare that to? Well, what I could compare this to is this position and then some position that is infinitely far away. Well, as r becomes closer to infinity, the voltage drops to 0. So the potential difference, if I were to compare it between this point and infinity, it'd be the same value. It'd be that negative 3.96 times 10 to the ninth. Now, once we've done this, we can start to make a map of the electric potentials for some systems of charges. So here I have a 9 coulomb charge, and if I chose a point here, so if I chose a point here, and let's say it's 10 meter or 1 meter away. So I would have 9 times 9 billion, divide that by 1. So it's this point would have a voltage of positive 8.1 times 10 to the 10th volts. If I chose, and notice that it doesn't matter where that charge would be on this circle. Everything on this circle has an electric potential of 8.1 times 10 to the 10th volts. And if I chose a different circle, let's say at 3 meters, well, I'd have 9 billion times 3, 9 billion times 9, divide that by 3, so that'd be 2.7. So everything on this line would have a voltage of 2.7 times 10 to the 10th. And we can develop this map. Now for this simple point charge, these lines would be, the same. Now we call these equal potential lines because everything on this line has the same potential. So now if I have a system of charges, let's say a positive 2 and a negative 1 charge, I can then use the superposition principle, and I could calculate a bunch, almost an infinite number of uh, potentials. So then what I could do is I can make a map of the voltage or the electric potential in and around each one of those charges. And it kind of looks like a topographical map. So in a topographical map, each line represents elevation, and the closer the lines are together, the quicker the slope of the hill rises. So it'd be sort of the same thing here. So that leads us into something called electric fields. Electric field lines are vectors, and they're just like gravitational field lines, but electric field lines are vectors that point in the direction of least electric potential. They represent the path that a positive test charge would take. And the electric field lines are always drawn perpendicular to the electric potential. So if I have a positive charge, I can start drawing the equal potential lines around it, and the electric potential will get weaker as I get farther away. So then the electric field lines would have to be perpendicular at all points. So these would represent the electric field lines. So for a positive charge, they diverge away. For a negative charge, it sort of looks the same, but since it's a negative charge, the electric potential gets lower as you get closer. So here the electric field would point toward the negative. And again, keeping it perpendicular at all points. So if I had two charges then, the equal potential line, so at exactly between the equal potential, the voltage would equal 0. And then it would look something like this. So then the field lines, the electric field, would look something like this, and being careful to keep them perpendicular to the equal potential lines at all points. So that would be the electric field between those 2 points. So if I look at, now this represents equal charges. So let's say this is plus 10 and this is minus 10 coulombs. So equal charges. So if they're unequal, then the electric field is going to look a little different. And all you have to do is keep the electric field lines perpendicular to the equal potential lines. So it kind of curves a little more drastically. It's like the positive 2 charge is overpowering the negative 1 charge. So a vector field gives, as a function of position and maybe time, the value of a physical quantity that is described by a vector. So vector fields are represented by vector fields, field vectors indicating the direction and magnitude. When we have more than one source, with mass or electric charge, the field value can be determined by vector addition, just like we've done in the past. And conversely, a known vector field can be used to make inferences or guesses about the number, relative size, and locations of the sources. Now, the way we calculate electric field is we take the electric force per unit charge. And these are all vectors here. So, electric force, let's say I have a big Q and I'm using a test charge to find out what the electric field is at that test charge. So I would have K, Q, Q over r squared, divide that by a q. So I find that the electric field would look like that. The units for electric field will be newtons per coulomb. So if we take a look at this, we see that the electric field should be a newton per coulomb because it's a force per unit charge. All right, sorry for the lengthy video, but that concludes this unit.